Ever wondered what will happen to the universe? Back in the 1930s and 50s, Edwin Hubble observed that galaxies are drifting apart. This led to the Big Bang theory, suggesting the universe began around 13.8 billion years ago. Since then, it's been expanding and becoming less dense, but will this ever end? One of the most chilling theories for the universe's ultimate fate is the Big Freeze, also known as heat death. The universe continues to expand, and as it does, it asymptotically approaches absolute zero temperature. This means everything cools down to the point where no significant heat or energy can be transferred. In this scenario, the universe reaches a state of maximum entropy. Everything becomes evenly distributed, and there are no energy gradients, which are essential for sustaining processes like life and information processing. So what does this mean for the cosmos? For the next 10 circumflex 12 to 10 circumflex 14 years, stars will continue to form as usual. However, eventually the gas needed for star formation will be depleted. As existing stars exhaust their fuel and cease to shine, the universe will slowly grow darker. Imagine a night sky with fewer and fewer stars until it's almost pitch black. In this dark universe, black holes will dominate, but even they won't last forever. Over time, black holes will evaporate through a process known as Hawking radiation, ultimately disappearing into nothingness. Over infinite time, some fascinating phenomena could theoretically occur. The Poincaré recurrence theorem suggests that, given enough time, the universe might experience a spontaneous decrease in entropy. Thermal fluctuations and the fluctuation theorem also point to the possibility of temporary, localized decreases in entropy. However, these events are incredibly rare and would not change the overall trend toward heat death. Interestingly, the heat death scenario can happen in any of the three spatial models of the universe. Without dark energy, it could only occur in a flat or hyperbolic geometry, but with a positive cosmological constant, it could even happen in a closed universe. Another fascinating and terrifying theory about the universe's ultimate fate is the Big Rip. Imagine a universe where the acceleration of cosmic expansion doesn't just continue, but actually speeds up exponentially. This is driven by what's known as phantom dark energy, a hypothetical form of dark energy with a negative kinetic energy. Currently, our universe's expansion is defined by the Hubble constant. This rate of expansion is not large enough to tear apart galaxies, which are held together by their gravitational pull. However, if the Hubble constant were to increase steadily to infinity, it could spell a catastrophic end for everything we know. In this scenario, the increase in the Hubble constant would start by separating galaxies from each other. As time progresses, the acceleration would intensify, eventually overcoming the gravitational forces holding stars within galaxies, planets around stars, and even atoms within matter. Picture this: galaxies disintegrating into individual stars, planets being ripped away from their orbits, and finally all matter breaking down into unbound elementary particles and radiation. This would culminate in a universe where the energy density, scale factor, and expansion rate all become infinite. Essentially, the universe would end as what is effectively a singularity. In the special case of phantom dark energy, this catastrophic end could occur even more suddenly. The negative kinetic energy associated with phantom dark energy would result in a higher rate of acceleration than other cosmological constants predict, leading to a more abrupt and violent Big Rip. There's another intriguing possibility that suggests a more cyclical nature to cosmic events: the Big Crunch. Unlike other theories that focus solely on expansion, the Big Crunch hypothesizes a symmetric view where the universe's expansion will eventually halt and reverse, the universe reaching a critical density where its gravitational pull overcomes the force driving its expansion. Instead of continuing to stretch outwards, the universe would begin to contract. Galaxies would start to move closer to each other. Stars would collide, and all matter would converge towards a single point. This process would culminate in the universe collapsing into a dimensionless singularity, a state remarkably similar to how it all began with the Big Bang. But the Big Crunch doesn't just end there. Some theories propose that this singularity could spark a new Big Bang, leading to a new universe. This creates a cyclic or oscillatory model where the universe undergoes an infinite sequence of expansions and contractions. Each Big Crunch would be followed by a Big Bang, giving birth to a new universe. However, this cyclic model faces significant challenges. The second law of thermodynamics states that entropy, or disorder, always increases over time. If each cycle accumulates entropy, the universe would eventually experience a heat death, rendering the cyclic model unsustainable in the long run. Moreover, current evidence suggests that the universe is not closed and will likely continue expanding indefinitely. Despite these challenges, some cosmologists propose a modified cyclic model. There is another theory that takes this concept even further, is the Big Bounce. The Big Bounce is a theorized scientific model related to the beginning of the known universe. It derives from the oscillatory universe, or cyclic repetition interpretation of the Big Bang, where the first cosmological event was the result of the collapse of a previous universe. According to one version of the Big Bang theory of cosmology, in the beginning the universe was infinitely dense. Such a description seems to be at odds with other, more widely accepted theories, especially quantum mechanics and its uncertainty principle. Therefore, quantum mechanics has given rise to an alternative version of the Big Bang theory, specifically that the universe tunneled into existence and had a finite density consistent with quantum mechanics, before evolving in a manner governed by classical physics. In the Big Bounce model, if the universe is closed, this theory would predict that once this universe collapses, it will spawn another universe in an event similar to the Big Bang after a universal singularity is reached or a repulsive quantum force causes re-expansion. In simple terms, this theory states that the universe will continuously repeat the cycle of a Big Bang followed by a big crunch. Each collapse would not signify the end, but rather a new beginning, a rebirth of the cosmos itself. Each possibility described so far is based on a very simple form for the dark energy equation of state. However, as the name is meant to imply, very little is now known about the physics of dark energy. If the theory of inflation is true, the universe went through an episode dominated by a different form of dark energy in the first moments of the Big Bang. But inflation ended, indicating an equation of state far more complex than those assumed so far for present-day dark energy. It is possible that the dark energy equation of state could change again, resulting in an event that would have consequences which are extremely difficult to predict or parameterize. As the nature of dark energy and dark matter remain enigmatic, even hypothetical, the possibilities surrounding their coming role in the universe are currently unknown. The mysteries of dark energy and dark matter challenge our understanding of the universe and its ultimate fate. They are the unseen forces that could hold the key to unlocking the secrets of cosmic evolution.